Perhaps one of the rarest of human experiences is discovering a new planet in our solar system. In 1846, the planet Neptune was discovered, usually credited to Urbain Le Verrier, though there were other independent discoverers around the same time. This discovery was made through studying perturbations in the motions of the planets. Something was tugging oddly on the planet Uranus. Le Verrier knew that there had to be another planet out there. Since then, no further planets have been found other than the discovery of Pluto by Clyde Tombaugh in 1930, which is really a Kuiper belt object of which many more minor planets have been found in recent years, but nothing large until perhaps now. In recent years, it has been noticed that some objects in the outer solar system are perturbed in such a way that another large planet is increasingly suspected to exist beyond the orbit of Neptune. My guest today is searching for this hypothesized Planet 9. In today's episode, John is joined by Dr. Konstantin Batygin, Assistant Professor of Planetary Science at California Institute of Technology. Dr. Batygin graduated with a bachelor's degree in astrophysics in 2008. He won the Lawrence Deck Award for his thesis on the dynamical stability of the solar system and is on the 2015 Forbes list of 30 scientists under 30 who are changing the world. Dr. Batygin, welcome to the program. Great to be here. Now, Dr. Batygin, this is what you're doing in looking for Planet 9. You're looking for the first planet we've discovered since, arguably, Clyde Tombaugh and Pluto, but certainly Neptune in, what was it, 1846? That's right, 1846. What led you to suspect that there may be a ninth planet in the outer solar system? Put succinctly, it's the structure of the distant solar system. If you go beyond the orbit of Neptune to the outer edges of the solar system, what lies beyond is a field of icy debris that is cumulatively known as the Kuiper belt. The first Kuiper belt object that was discovered, as you already mentioned, was actually discovered by Clyde Tombaugh, and that is Pluto. Pluto is a member of a much broader population of icy objects known as the Kuiper belt. If you look at the most distant orbits within the Kuiper belt, these are things that take 10,000 years to revolve around the Sun one time, then what you will note is that all of their orbits point in the same direction roughly and they kind of lie in the same plane. It looks like something is corralling them into a group, into a cluster. What that structure is telling you is that there's a gravitational influence beyond the 8 known planets of the solar system, and there indeed exists a ninth planet, which lives far, far away. How far? Our current best estimates place it at an orbit where the mean distance is about 500 astronomical units, so 500 times more distant from the Sun as the Earth. This puts it on a similar orbital period as some of these very long-period Kuiper belt objects, also about 10,000 years. So a 10,000-year orbit. This would probably be a very elliptical orbit, would it? Yes, the orbit is unlike those of the rest of the solar system. The rest of the solar system orbits are pretty circular, maybe out of round by a few percent, but nothing too significant. Planet 9 has an eccentricity which is substantial. It's at least 20%, probably more like 30%. An eccentricity of 0.3. We used to think back 3 years ago when we first made the announcement that it was actually more eccentric than that. In the first couple papers, I used an eccentricity of 0.6. Over the last couple years, I've done a tremendous amount of calculations which kind of lowered that best fit by a factor of 2 or so. An eccentricity of 0.3 is kind of standard if you look at planets around other stars, so exoplanets very often will have eccentricities of order 0.3, but it is indeed unusual for a solar system object. So it would have an eccentric orbit, meaning that it would pass closer to the Sun at certain times and further away from the Sun at others. I suppose that's called the semi-major axis. How far and how close does it get to the Sun, do you think? That's a great question. At closest approach, it gets down to maybe 300 astronomical units, maybe a tiny bit less, maybe 290, but you really can't push it below that without ruining the outer solar system structure that we observe. We know pretty well that its closest approach is about 300 astronomical units. Its furthest approach, what we call aphelion, is somewhat less well constrained. That's because in the calculations, there's a degeneracy between the semi-major axis and eccentricity to an extent. I can make the orbit of planet 9 slightly bigger at the expense of making it slightly more eccentric and still match the data pretty well. To give you an overall sense, at aphelion, its furthest point is going to be about 650 astronomical units. Now what does that tell you about the size of this object? What's remarkable is that we don't know anything about what Planet 9 physically looks like. All we know, all that the calculations give us, is the mass. That's all that matters for gravity. That said, 5 Earth-mass objects are exceedingly common around other Sun-like stars. As it turns out, this is maybe one of the main takeaways from the Kepler mission. The most common type of planet in the galaxy is a 5-ish Earth-mass object. These bodies tend to fall into 2 different categories. Some of them are only a factor of 2 bigger than the Earth, and others are quite a bit bigger, maybe a factor of 3. We really don't know what the physical radius of Planet 9 is, and that's what makes the search so attractive. We're looking for something that we really have no physical Bayesian prior for, we don't know what we're going to find. That's always been somewhat of a mystery since Kepler. Why does the solar system not have a super-Earth? Absolutely. This could be our solar system super-Earth that perhaps got ejected early in the history of the solar system. If that's the case, what kind of planet would this be? What might it look like? As far as the best guess for its physical structure, I think it would be an object with a large icy core, so to speak. It's a big ice ball, kind of like Uranus and Neptune, engulfed in an atmosphere of hydrogen and helium, probably, and this is just an educated guess informed by exoplanets, something like 3% or 10% by mass. If I were to take a guess, I would assume that it's 5 Earth masses of ice and rock enveloped by a fraction of an Earth mass in a kind of extended hydrogen-helium atmosphere. The remarkable thing about an atmosphere like that, placed very, very far from the Sun, is that it should be quite reflective. Theoretical models tell us that such an atmosphere should be basically what's called a Rayleigh scatterer because most of the condensables are gone from the atmosphere. Again, we're getting into more speculative aspects of the theory. You say reflective, which implies that it would be more detectable. Of course, this is not an easy thing to detect. How do you narrow it down? How do you find Planet 9? Great question. The short answer is it's extremely challenging. We don't know where Planet 9 is on its orbit, and the reason we don't know that is because the only observations we have of the distant solar system are the Kuiper belt objects themselves, their orbits, not the full arcs. As I mentioned earlier, it takes 10,000 years for these objects to go around the Sun, and we haven't been alive that long. At the end of the day, we simply don't know where it is on its orbit, but we can use other constraints to rule out fractions of the orbit. One interesting constraint is spacecraft trajectories. Planet 9 at closest approach would be at about 300 astronomical units, and as far as we can tell, that would give rise to a detectable deviation of, say, the Cassini spacecraft over its course, and that is not seen. So we know it's not at perihelion, its closest approach. It would also be bright enough to be detectable by conventional surveys at perihelion, so we kind of know it's not there. We rapidly lose precision as you move further and further away from the Sun along the orbit. Our best guess is that it's close to aphelion, the most distant point along the orbit. That more or less must be true, not must be true, but it's likely to be true simply because on a Keplerian orbit, you spend more time at aphelion. Ultimately, we are stuck with the problem of having to explore a pretty large swath of the sky. That's interesting. You mentioned the Cassini spacecraft. We can actually detect noticeable gravitational deviations from spacecraft that are in or were in the case of Cassini in the solar system. What about New Horizons? Can you see from that? New Horizons, not so much, because New Horizons is headed in the other direction. The advantage with Cassini for this type of calculation is that it was in orbit for a long time, so you have a large arc of the Saturnian orbit to pretty good precision. There are still complications that arise, namely how do you properly account for all the maneuvers. Every time you introduce non-gravitational accelerations, you have to somehow account for that in the model, which introduces errors. This is still very much an ongoing problem, but it is clear that if Planet 9 were at its closest approach to the Sun, you would see a detectable perturbation onto Saturn and, by extension, onto Cassini. Do you see anything with Uranus and Neptune, any abnormalities in their orbits that made people in the past think there might be a planet out there? No, and that's simply because the data isn't good enough. With Cassini, you get something like 100 meters precision, which is astonishing. We just don't know the orbits of Uranus and Neptune to such high precision, especially over long periods. A lot of this information really does come from spacecraft. You would need to put a spacecraft in orbit around whatever planet you're interested in and then wait for the planet to make a substantial arc around the Sun. Of course, the orbital period of Neptune is 164 years, so that's quite a few decades of data collection. What instruments are you using to look for Planet 9? The primary telescope that we're using is the Subaru telescope. The Subaru telescope is the Japanese National Observatory. It's an amazing 8-meter instrument with a huge field of view. The reason Subaru is so useful is that its field of view is large enough to cover a large swath of the sky all at once, which is something that we require for the search. Even with this amazing instrument, however, it is taking us a long time to cover our search area. We have a lot of new telescopes coming, interesting new instruments like the Large Synoptic Survey Telescope, LSST. If you don't find it with the Subaru telescope, do you think that you'll nail it with things like the LSST? Yes, I think that's right. LSST will go down to magnitude 23.2, something like that, and importantly, it will survey the sky multiple times. If we don't find it by 2022 or 2023, I think LSST will answer the question. It will either directly find Planet 9, or at the very least, it will find probably 100 of these long-period Kuiper belt objects. From that point of view, we'll be able to do much more precise modeling and constrain the orbit even better. Finally, it will place observational constraints on the orbit. 1,000 images is not a particularly difficult thing to do. Do you do any citizen science? I know that with Kepler there was the Planet Hunters project where people could actually look manually for transiting exoplanets. Have you done anything like that? Yeah, so with Planet 9 search we haven't yet, because in part because we've been basically data limited, right? We got good data back in September 2017 and analyzed that, and the first time we got good data since then was this past December. So for now we don't really need the citizen science help, but I think that's going to be a huge thing once LSST comes online. So I think it's more of a issue of how much subscribed data we have to play with. So we haven't done that yet. We might do that in the future, and on that we have to go to a break. I want to remind everybody to hit subscribe and click the bell for new episodes of this show. We'll be right back. We upload videos every Thursday plus additional content. Dr. Batygin, welcome back to the program. Thanks for having me back. This idea of captured planets, so it's constrained. We can't exactly say that there are 10 planets out there. There must only be 1 or 2 at best, right? That's right. And in fact, even if you suppose you don't know anything about the Kuiper belt, right? Suppose you've never seen the Kuiper belt, you can still ask the question of what is the kind of parameter space that remains in the solar system where you could put a planet and get away with it. And that's a calculation that we've done, and it's going to be in an upcoming paper, called The Planet and Hypothesis, the review paper. And as it turns out, if you just do this calculation, kind of accounting for, okay, you can't mess up the trajectories of spacecraft, you can't mess up the observational surveys. Meaning that, there are constraints on bright objects far away from the sun, and also you can't put things so far away that they would get stripped away by passing stars. You get a relatively narrow range of parameter space, and then if you ask where does Planet 9 fall in that kind of island, it falls smack in the center of it. So it's actually an interesting exercise to do, just because it's a completely kind of model-independent assessment of where could planets be in the solar system that we haven't yet found. One thing I've noticed About following while following the story is that it seems that more and more objects are being identified that have these weird orbits that are suggestive of this planet. What is your sense? I mean, is it possible that it's not there or are you convinced that it really is this? This must be yeah, so there's is planet 9 there? I used to always answer this question by saying that I am something like 6 billion per sure that planet 9 is there. But the more correct answer is that there is indeed a false alarm probability to all this, right? And that probability is addressing the question of how likely is it that all of these distant orbits that we see that appear to be clustered together in space are just so by chance, right? And there's a very well-defined answer to that, and the answer is 0.2%, so I am 99.8% confident that planet 9 really is there. Now say you find it and we have a ninth planet again, depending on what people feel about Pluto. So we find it. What does this tell us about star system dynamics? Can we look for exoplanets outside of our solar system? Does it suggest that this is a common phenomena, that where you have these weird eccentric outer planets orbiting stars, and could be common? Does it give us any information on that, on the study of exoplanets? What a great question. Yeah, so I think this is something where it becomes immediately intriguing. Does it immediately tell us that every sun-like star should have a planet 9 equivalent? Absolutely not, because progressively it looks like the solar system itself is kind of an oddball against the galactic backdrop of planetary systems, right? Jupiter-like planets are rare. We don't have a close-in system of super-Earths. Just the solar system is messed up when you compare it with a typical planetary system in the galaxy. So does solar system having some object like planet 9 tell us anything else about the galaxy? No, but I think what it would immediately demonstrate, or rather the constraints that it would entail, would all be on the early formation of the solar system. We don't really understand at the details level the early formation of the solar system. I mean, that's just a true statement, and discovering planet 9 and characterizing it will yield constraints that we right now just can't imagine. So it'll be huge. It'll be a huge improvement in our understanding of the origins of our cosmic home. Yeah, the solar system does seem weird. No super-Earth, and then it's got a rare gas giant. How does Saturn play in? Is Saturn sort of like Jupiter? Is it rare? I mean, is that a rare object? Yes indeed. So both Saturn and Jupiter are strangely uncommon if we believe the current narrative for solar system formation, and this narrative is subject to change always. But the current kind of iteration of narrative, much of the solar system's early evolution was actually shaped by the gravitational interplay between Jupiter and Saturn. So we would have had a very, very different planetary system if we only had one of them. So there's all this detail which for now, we're just as planet formation theorists just shifting through, right? And we're not, really it's only been in the last decade and a half that we've began to really uncover the role that Jupiter and Saturn's early migration, their movement through the solar system played. So there's just a tremendous amount of work left to do in this domain. Now this is somewhat of an offbeat question, but if one of the ways that astronomers look for exoplanets is as the radial velocity method, where you're looking for wobbles in the start. Is planet 9 too far away for us to have a measurable effect that we could look at with regarding the sun's movement? Yeah, that's right, and really the answer that is yes, the movement itself is tiny, and also that movement is happening over the orbital period of the planet, right? So it's taking that reflex velocity of the sun. In order to see it, you'd have to observe the sun for 10,000 years, and although I am indeed planning to live on as a cyborg forever, for now that type of observation is out of reach. Watching the sun for 10,000 years looking for a planet, now you say you want to live on as a cyborg. Are you sure you would? You rather just live on as uploading yourself into a computer rather than becoming a horrible cyborg? Yeah, what a great question. Yeah, I mean, I haven't given this sufficient thought to really make the distinction. I don't know, maybe I prefer to be just software. No, actually, now that I really think about it, I think I prefer to have some hardware too. Well, I would imagine you could switch back and forth if you